First of all, so welcome. This is our, I believe it's our 7th session, Tuesday of the 4th week. I believe it's our 7th session. And let's start by going over some homework questions. So I have the sapling open. So good to go. Okay, so which question in particular?
I'm logging in right now.
Okay, no problem.
I believe it was question 9 for homework 3.
Okay, so someone sent me a text. He's trouble on question 3, and you're saying question 9. Let's start with question 9, because I happen to be at question 9 from someone in my office hours. That's the sulfur dioxide one, correct?
Yes, I was just trying to figure out the proportions.
Okay, for what? You're talking about part A, part B, part C?
Part B.
Okay, part B. So let's take a look at it. It says if the distribution is really n of 5.43.54, what proportion of observations will be less than 5.05? So do you use Crunch It for that?
Yes, I believe I started using Crunch It for it, but I felt like Crunch It gave me a specific answer. I used both Crunch It and the table.
Okay.
For like scores.
Okay, but the table you switched to Z scores, correct?
Yes. But whatever proportion I got, it still counts as wrong.
It said the calculation was wrong. Okay, well, let's do it. So first, let's compute the Z scores, or the Z score. What is the Z score for this situation? And tell me how to get there.
So for the first one, I think if it's less than, it would be 5.05 minus 5.43 divided by the standard deviation, which is 0.54.
Okay, so when you do that, what do you get?
Get my calculator. Negative 0.703.
Negative 0.703, negative 0.704 actually is a little bit closer. But since your calculator can only do 2 decimals anyways, we'll just stop it at negative 7.0. And then, I mean, they want your answer rounded to 4 decimal places. So unfortunately, a table is probably not going to be accurate enough. And we have to do Crunch It. So I'm going to share my screen. Can you all see what I have here? No, that's the answer. Yes. So let's not use that. So let's go to, so these are the, okay. So let's remember, so this is n of 5.43 comma 0.54. And we want less than or equal to 5.05. So let's get out of here. Okay, and let's go to Crunch It. How do I get the, hold on, let me stop sharing for a second so I can see it on my ends. Find Crunch It. Okay, so I'm going to start sharing again because I now have Crunch It. So, okay, so here's Crunch It. Okay, all right, let's get this out of the way. Oh, I'll just show this down. Okay, so here's Crunch It. So we are going to go to the distribution calculator and we're going to go to normal because we have a normal distribution, correct? Yes?
Yes.
Okay. The mean as given was 5.43 with a deviation of 0.54, correct?
Mm-hmm.
And we want less than or equal to 5.05. And then we go to calculate. So it tells us that the answer should be 0.2408. Now 0.2408 is what I had on my calculator. So, I mean, on my screen, that's what the program said was the correct answer. So is that not what you had?
I did end up getting like 0.2327, but that's probably because I got a number that was off. But I put it
But
in.
0.32 is really far off from 0.24. That's not an approximation mistake. That's doing something wrong mistake.
Okay.
I'm not sure what you did wrong. I'd love to see your work to know, but that's too far away. You see what I'm saying?
Mm-hmm.
0.32 is that's, I mean, it's an 8% difference. That's not an approximation. Approximation would be like 0.5%, something like that, maybe. So does that make sense? What I'm trying to say?
It does.
Yeah.
Would I put in the answer as like 24.08 or just 0.2408?
Well, let's take a look. So when I go back to the, oops, when I go back to the chapter 3 homework, and I look at question 9. So their answer is just 0.2408.
Okay.
And it says, I'm sure they would, I don't know the program, but they would probably accept 24.08% if they had a percent key. Does that make sense what I'm saying?
It does. Thank you.
Okay. Okay, so there were some other questions. I'm going to stop sharing. And I had trouble on question 3. So let's look at question 3 now. Okay, so let's start sharing again. So question 3 says, almost all medical schools in the United States require students to take the medical college admission test, the MCAT. A new version of the exam was introduced in spring 2015 and is intended to shift the focus from what applicants know to how well they can use what they know. One result of the change is that the scale on which the exam is graded has been modified, with the total score ranging from 472 to 528. And in spring 2015, after they switched it, the mean score was 500 with a standard deviation of 10.6. So use table A to find the answer to the two questions. What proportion of students taking the MCAT had a score over 510? This is data, right? This is not, where's table A? Okay, maybe it's not data. It sounds like data. Forget about the answer, ignore the answer. It says, what proportion of students had a score over 510? Oh, the mean score was 500 with a deviation of 10.6. So we are using the data. So let's go back to crunch it. Okay, let's go back to crunch it. What was the mean again? The mean was 500. So the mean is 500. And the deviation was 10.6. And it says we want to know what proportion had a score over 510. So we can't put in 510 here because this program does less than and we want greater than, correct? Correct?
Correct.
So if I want less than, if I want greater than, I got to switch it. And when I do, it goes 510. And when I calculate, it gives me 0.1727. 0.1736.
I put that in and it still said it was correct.
Oh, okay. But that's interesting that it would be off because it was 510.6, 510.6 greater than 510. Interesting. Anyways, does that make sense for that one?
Yeah, that makes sense.
Okay. And then what proportion were between 505 and 515? So this we got to do in 2 stages. I can do more than 505 and I get that number. I can do more than 515 and I get that number. And then once I have those two numbers, what do I do to them?
Average subtract each other.
Well, no. remember how we use this normal distribution. What was the mean again? 500?
Yeah.
Yeah.
So here's 500. And we want between 505 and 515, right? Correct?
Yeah.
So if I compute more than 505, which gives me all of that, and I compute 515, which gives me all of that, if I want this part, I take whatever this number is and I subtract whatever that number is. Right?
Correct.
All of this, take away that, gives me what's left. Right? Communication? Yes, no?
Yes.
Ryan, the questions could be randomized. So you might have the same question, but not precisely the same, if you know what I'm saying. So as long as you understand how to answer it, then yours will be similar. And then this very question, someone said, oh, okay. Someone said for question 7. So let's just quickly look at question 7. Question 7 says, let me share my screen again. So question 7 says the common fruit fly, Drosophila melanogaster, is the most studied organism in genetic research because it is small, easy to grow, and reproduces rapidly. Nobody cares. Anyways, well, they care, biologists, I guess. The length of the thorax is in a population of female fruit flies is approximately normal with mean 0.8 and deviation 0.078. What proportion of flies have a thorax length less than 0.68? We would do the same thing. What is that same thing? You go to crunch it, you put a mean of 0.8, a deviation of 0.078, and you want less than 0.68, and whatever pops out, pops out. I mean, right? At this point, these questions are very similar. Does that make so part C, she says. Okay, so let me go back. See what part C says. So so this is the same thing. What proportion is between 0.68 and 0.87? You do less than 0.87, you do less than 0.68, and you subtract them. Right? It's the same idea as the other one. Right, Ryan?
Yeah, I got it now. Thank you.
Okay, Lee, does that make sense? Leah? Okay, good. All right, so let's go to, I am recording. Okay, good. Let's go to PowerPoint, chapter 3. Have we finished chapter 3 at this point, the normal distribution? Is there any part that we haven't done yet? I don't remember. I don't remember. Did we finish chapter 3, guys? Does anyone remember where we left off?
Last couple of slides.
Well, okay, so does anyone recall the slide that we did last? Where we ended up? Well, here, let me show you some, and you can say, oh yeah, I recognize that one. Did we do this one?
Yeah.
Okay. And after that are just questions. So yeah, we did finish. The rest of them are just lots and lots of questions and normal calculations.
I think we didn't do normal calculations.
Well, no, we didn't go through this because this is your homework. Your homework is just lots and lots of examples of calculations. These are all just problems directly from your textbook. But what we can do very quickly is we can do one of them. Let's do. Okay, let's do 3.21. So it says the scores of an IQ test are approximately normal. Yes?
Yeah.
Okay, with mean 100 and deviation 15. Alicia scores 135 on her test. What is her Z-score? So how do you calculate a Z-score? You need 3 pieces of information: her data, the mean, and the deviation. Do we have all 3 of them?
Yeah.
Yes. So let's go ahead then. I'm going to stop sharing now because you guys should have your own PowerPoints loaded up. Hopefully, this is slide number, this is the last slide, 35. So what is her z-score? How do you calculate her z-score? Anyone? Say it out loud.
Her score minus the mean over standard deviation.
Exactly. Her score, her data, x, minus the mean. The mean is 100 over the standard deviation. So what's her score?
2.33 repeating.
Oh, that's her z-score.
Yeah.
Right. Her score is 135. So 135 minus 100 is 35. 35 divided by 15 is 2 1/3, 2.33 repeating, right? So the follow-up question is 3.24. She scores higher than what percent of adults? She scores higher than what percent of adults? How would I calculate that? She scores higher than what percent of adults? This is the key. Her z-score by itself tells us, I mean, yeah, it's good to know, but at the end of the day, we're curious, where does she fall in the grand scheme of things? She falls in the grand scheme of things by how well she does compared to her peers. So what percent of adults does she score better than is the question. So how do I calculate that?
You get it from the data because of her z-score. Like you go to the chart.
So you don't get it from the data technically, you get it from the z-score.
Yeah.
Which is arrived at from the data. Ryan, you say 2.9788. I'm not sure what you mean by that. You can say it out loud if you want.
When I was looking at the table, that's what I got from the z-score.
Well, the z-score is 2.33.
Oh.
All right, 35 over 15, right?
Yes.
All right, so the question is, how do I use that z-score to answer the question, she scores higher than what?
99%.
Where you get that from?
The table under 2.33. That's what the number is. And then you put that into a percentage.
Wonderful. So there's two ways of doing it. One way is to go to the table, which is totally fine. What is the disadvantage of the table? Well, you first have to find a table, and then it's only going to be an approximation. Whereas computers and something like Crunchit is going to be more accurate. So let's load up Crunchit, since we have it up anyway. And let's put it in. What's the mean here?
100.
Well, if we got a z-score, then the mean is now 0 with a deviation.
Oh, okay. Yeah.
Right?
Yeah.
And we're looking for x less than or equal to hers, which is 2.333333. And if we calculate, we see that it's about 99%, which is a slightly better approximation than the table gives us, correct?
Yeah.
If we would use the actual data, which is 100, 115, and a value of 135, it'll probably be very close to this. Oh, not 115, 15, sorry. And you see, it's pretty much indistinguishable. I mean, I don't know. I don't know which decimal it was because I already forgot. But that seems fairly close, right? Correct?
Yeah.
Okay. So let's look at this last one, 3.42. It says weights are not normal. The heights of people of the same sex and similar ages follow a normal distribution reasonably closely. Weights, on the other hand, are not normal. The weights of women aged 20 to 29 in the US has a mean of 161.9 and a median of 149.4. What does that tell you about the symmetry or skewness of weights?
It's skewed to the right.
Skewed to the right.
Because the mean is pulled to the right.
Because the mean is pulled to the right, right? If the mean is pulled to the right, the mean is greater than the median, then we know it's going to be skewed to the right, correct? Now, the first and third quartiles are 126.3 and 181.2, correct?
Yeah.
So let's draw the 5-number summary, or let's draw the box plot for this. So we're going from 0 to 200, let's say. Here's 0, 200, 100, 50, 150 or so. The median is 149.4. So the median is about there. The third quartile is 181.2. The first quartile is 126.3. We don't really have the min and max. I'm not sure why I'm doing this, but the mean is about here, 161.9. But I just realized as I was doing it that we don't have the min and max, so you can't really do the 5-number summary. You can't really do the box plot. But they're asking about the shape. The mean is pulled to the right. It's skewed to the right. Not normal. Okay. So are there any questions on chapter 4? Chapter 3, I mean. Are there any questions on the third chapter? The normal distribution. We use crunch it, and we calculate either probabilities if you have numbers if you have probabilities. We can go either way, and also converting data to z-scores, right? You got to be able to go in both directions. Data to z-scores to probability, or probability to z-scores to data. You should be able to go back and forth. So if there are no further questions, I'm going to find and load up now the 4th chapter, put it on Canvas, and then we'll jump right in. Sound good?
Mm-hmm.
Just give me a second. Here we go. Loading up chapter 4 PowerPoint. Okay. Oh, chapter 4 and 5, it looks like. It looks like it's one PowerPoint for both of them, which means, this is awesome, we get to do 2 in 1. All right, isn't that exciting? Move to desktop, save. File. Okay, it is downloading. Give it 10 seconds, and then we will be good to go. Okay, it is up. Please load up the chapter 4 and chapter 5. Oh, wait. No, hold on. I don't think that was it. I'm deleting that quickly. I don't think that was it. I don't think that was it, because it said key to it, and I think key means something else. I'm sorry, give me 1 second. I apologize. No, I don't think this is it. Hold on. Oh, I think that was it. Okay. Okay, downloading again. Five, four, three, two, one, and go. Okay, so let's load up the chapter 4 and chapter 5. It says 4 and 5 regression and correlation key. Please tell me if it's not downloadable. It's not a PDF, but it says key. If anyone has any problems, I can always convert it to a PDF. Maybe I should do that anyways. Can I stay? Of course, you can always stay for office hours after class. I stay in here until my next class starts, which on Tuesdays and Thursdays is 6:30. So I'll be here.
It says that I can't access it, Professor.
I'm sorry, say it again.
It says that I can't access it.
Okay, so I'm going to make it a PDF instead. And now I'm going to delete the one that's on there. I'm going to delete it because obviously that's not the right one. So sorry, delete.
I was able to open it, but it wasn't the same format as the other PowerPoints. Or like, it didn't look the same as the other ones.
Yeah, it looks a little different. It does look a little different, but I did make it a PDF. So let me put that on it instead. How do I know which is let's try this one. Let's see what happens when I do that one. Excuse me. Oh no, that's the same one, so it must be the other one they want. Okay, PDF up there. So you should be able to load the PDF now. Do you all have the PDF?
Yeah.
Okay, so let's start. So this one is, so we're now starting chapter 4 and 5, which are very similar. They're connected. 4 and 5 are on regression and correlation. So up until now, we have focused our attention on one variable at a time, correct? Everything that we've done now has been a single variable. Is it normal or not normal? Is it right skewed? Is it less skewed or symmetric? What's the mean? What's the median? What's the mode? Right? These are all questions that we've asked about a single variable, correct? Regression and correlation is when you connect two variables together. And you start asking questions like, does one variable correspond to another variable? If I change the first variable, how will that affect the second variable? If you make one bigger, will the other one get bigger? If you make one smaller, will the other one get smaller? Will it do nothing? If it does get bigger, does it get bigger in a predictable way? Here's an example. If you're measuring the height of a child, do you expect that the length of time that the child has been alive to be a relevant factor in how tall the child is? Do you expect to have a correlation between them, that one and the other one are connected? Does that make sense? Yes? No? Am I talking nonsense?
Yes.
You guys hear what I'm saying? It certainly seems reasonable, correct? Now,
Yeah.
Can you predict precisely how tall a child is based upon their age?
No.
No, everyone's different. But you can certainly get an overall idea of the relationship between age and height. And you expect that as one gets bigger, the other one gets bigger up until a certain point, right?
Mhm.
Now, is that relationship linear? Do we expect children, when you compare their age to their height, do we expect all those values to fall exactly on a precise line? Or will there be some fluctuation about that line? Or will it not even be a line? Maybe it'll be a curve of some kind and not a line at all. Are these are questions that we might want to ask and we might want to attack mathematically. This is the concept of regression and correlation. Regression is the mathematics involved, and correlation is more the conceptual ideas, although there is math involved in that too, about whether or not two variables are connected. Okay, so let's start at the very beginning. We know that there's two types of variables, okay, categorical and quantitative, right? We've already talked about this, categorical versus quantitative variables, correct? What are categorical? They're the categories, right? Category 1, category 2, category 3, and so on. And what are the quantitative ones? They're ones that you can do math on. We want to take this one step further and be slightly more systematic about the types of variables that we can be dealing with here. So amongst the categorical variables and amongst the quantitative variables, we're going to be more precise. Let's do the quantitative variables first on the right side of the PowerPoint. So numbers that have mathematical connections form or come in two different types: discrete versus continuous. The basic idea of discrete numbers is that the numbers are separated, that there is a gap between any two numbers. So for example, if I say how many eggs are there, then there's 0 or 1 or 2 or 3, right? These numbers are discrete. They are separate and there's no continuity, right? There's gaps in between them. Would you agree? Okay. Versus continuous, which is from here to there and anything in between. So if I talk about the height of someone, you might say, oh, they're 5 feet or 5'1" or 5'2" or 6'3" and so on. But if you really think about it, every number in between is also a possibility. Right? It's not just 5'1" and 5'2". It's 5'1½". It's 5'1⅓". It's 5'1⅓". It's 5'1 2/7. In reality, you can get closer and closer and be more precise for all of them, correct? In that situation, we say it's continuous. Now, even when you have continuous data, you can't always, we don't have the technology to be that precise, right? So when we're actually measuring, we might not be able to do any better than to the 1/8 of an inch or the 1/16 of an inch or whatever the case may be. But theoretically, it can be infinitely, right? You can be infinitely precise if you had the technology to do so. Would you agree? Okay, so the difference between discrete and continuous. So rainfall, how much rain fell this year? They might give you an answer in inches, 2.7 inches, but in reality, what's the actual value? It could be 2.7, 2.1, 6.9, 8, 4, 7, 3, 5, and so on. We might not be able to calculate that, but theoretically it still exists. So does that make sense between continuous variables, quantitative variables versus discrete? Very conceptual idea, right? I'm not saying we're going to do different math depending if it's discrete or continuous, although we will. But just right now, conceptually, does that make sense, the difference between continuous and discrete? So if you look at their examples of discrete, number of keys, shoe size, even though they're not saying your actual length of your foot, but your shoe size, right? Shoes only come in very specific sizes. Yes, discrete, well, so someone asked, who says, discrete would mean that there can be a gap in between the numbers. That's a very good way of thinking about it. I will readily admit, for anyone who's going to be listening to this video later, that it's not accurate, that it's a little more rigorous than that. But for our purposes, it's good enough. That's what discrete means for our purposes. Okay, that you can, basically that you can count them. The first one, the second one, the third one, the fourth one, the fifth one, the sixth one, and so on. You can't count all the numbers in the number line. There's too many of them. They're They're too tightly packed. Okay, but if you can count them, then it's discrete. Okay, so if you look at these examples here, discrete, number of keys, shoe size, interest rate, versus continuous, height, which is everything in a whole range, weight, everything in a whole range. It says here GPA, but GPA really isn't continuous. That's a mistake. I mean, I guess it depends on how many courses you take, but your GPA, unless you take, I guess GPA would be continuous if you allow an infinite number of courses. But in reality, you know, if you only take 120 units, then GPA is technically discrete. Again, I'm not going to ask questions that are vague. So let's now go to categorical. Okay, and even in categorical, there's distinctions between what are called nominal versus ordinal. Nominal categories is something that has no order, right? Ordinal, order. Nominal, no order. I guess that's a good mnemonic. So eye color, there's no order. Gender, male, female, female, male, it's the same thing. Race, marital status, state of residence. They're categories, but there's no first category versus second, or this is better than that, or this is ranked lower than that. It's just categories. It's nominal. It's purely in any order is fine. But if you look at the second one, like the exam grade A, B, C, D, or F, you know, this many A's, this many B's, this many C's, it is categorical, but there's an associated order, right? A is better than B, which is better than C, which is better than D, better than F, and so on. Does that make sense? Questions on any of these? Right, military rank, general, colonel. Okay, let's go the other way, because I know that one, I think. Private, corporal, sergeant, lieutenant second grade, lieutenant first grade, captain, major, lieutenant colonel, colonel, general. See, it's all the order. It's like the alphabet, you know? The cop pulls you over and says, say the alphabet, and you're like, no problem. They say the alphabet backwards, and I'm like, I can't even do that when I'm sober, you know? So sometimes the way you say it in our heads is the way it's easier versus the other one. So does that make sense for the first one? The difference between the two types of categorical variables and the two types of ordinal. Categorical could be nominal or ordinal versus quantitative, which can be continuous or discrete. Any questions on that? Now's the time to ask privately or publicly. I'm okay with either one. Okay, so it says here the type of variable determines which graphical displays and summaries are appropriate. We already know that's true about categorical versus quantitative. And the claim here is that even within that, nominal versus ordinal, you might have a different way. For example, if I'm doing eye color, I can do them in any order I want. But if you're doing A, B, C, D, F for grades, it would be kind of weird to do it in some weird, strange order, would it not? Versus either A through F down or F through A up, right? When there's an order, you display them in order. It makes more sense to do so, okay? So next slide, page 3, it says spreadsheets, right? So collected data is often entered into a spreadsheet like Microsoft Excel. Has everyone here at some point in their life used Microsoft Excel?
Yes.
Okay, has anyone never used a spreadsheet program like Microsoft Excel? I've been using Microsoft Excel now for, I remember learning it, I must have been 12 years old, give or take. So we're talking about like at least 7 or 8 years that I've been using it, right? A long time. So you guys have probably used it for a long time as well. Google Sheets, see, a lot of the things that you guys do is new to me. You know, Google Docs, Google Sheets. I think Google Sheets is an is a spreadsheet program, but I don't know, to be honest. But I think that's what it is, right? Isn't that what it is? You can like put in numbers in 2 different cells and tell it to do things to them. So yeah, okay. So for example, suppose I ask the following questions of a group of students. What is your height in inches? Are you male and female? Are you liberal, moderate, or conservative? How many children would you like to have? I can make a spreadsheet on the very next page. Take a look at this spreadsheet. This is what slide number 4 now. And if you look at the spreadsheet here on slide number 4, right, we have the columns are labeled by the variables, or the variables: height, gender, your political orientation, and the number of children you want to have. Your values for the height are in the first column. Values, not values, but remember that's a categorical variable, but M or F for male or female in the second one. Your political orientation. Notice if there's a blank one there for the first one. What do you think the blank one means? What does that blank space mean for the first one? What do you think that means? Oh, someone's probably typing something. No, no one's typing anything. What do you think the blank space means?
You mean like it wasn't disclosed?
Yeah, either it wasn't disclosed or maybe you lost the information. I don't know, but you don't have it for whatever reason. And everything else is there. Okay, so for the 4 variables, determine if one is categorical, and if it is, nominal versus ordinal. If it's quantitative, if it is discrete versus continuous. So they gave me the answers, which sucked, but okay. Height. Height is quantitative. It's technically continuous, but because you don't say, oh, I'm 5 foot, 7.326948439 inches tall, you round, and when you round it, it becomes discrete, but technically it's continuous. Gender is certainly categorical, and there's no order to them, so it's nominal. Political, again, categories with no order, it's nominal. And how many children you want to have, that's quantitative, and unless you're Solomon and you're, that biblical story of cutting the baby in 2, we only have discrete values for number of children. Do we agree to that?
Yeah.
Okay.
Yes.
So let's look now at the next slide. It says, after doing graphs and numerical summaries on one variable, then you might want to examine the relationships between variables. For example, do you think height and gender are related?
Yes.
Okay, yes. Men are statistically taller than women, so height and gender are probably related. Do you think gender and political orientation are related? Should there be a connection between gender and political orientation?
No.
No.
Well, I don't know much about politics. It's certainly an area that I know nothing in. I readily admit that. I don't even really know the difference between a liberal and a conservative and a moderate. People tell me, and I'm like, oh, okay, I get it. And then the day later, I forget it because I really couldn't care less. But maybe it's possible that a certain gender is more inclined to a certain orientation than the other. I don't know. I honestly don't know. But if I was sufficiently inclined, I might want to do a statistical study to see and do an analysis. But I have no idea. Their answer here is maybe. Maybe. But I guess that's a great answer, maybe. I don't know. I have no idea. And then what about height and children? Do you think that there should be a relationship between how tall you are and how many children you want to have? Does that seem like it should be connected mathematically?
No.
No.
I don't think so. I don't think tall people are more or less inclined to have children than short people. And if I did a mathematical study on this, presumably I would show that mathematically there's no correlation. There's no connection between them. And if I did get one, I might want to start examining and try to figure out why. So in this chapter, we're going to focus on the relationship between 2 quantitative variables, and that is key. What we're doing now is specifically for quantitative variables. So that question that I just asked, which is there a connection between gender and political orientation? We are not answering that question in this chapter. Okay, why are we not answering that question in this chapter? Because political orientation is categorical. In this chapter, we are dealing with 2 quantitative variables only. Does that make sense? Are there any questions on what I mean by that? No? You sure? Okay. So let's look at the next slide. First, when you have two quantitative variables, they're not equal in the sense that well, how do I rephrase this? Essentially what we're looking at is, does one affect the other? An example would be how much studying you do and your scores, your GPA. Do you expect that the amount of studying affects your GPA, or your GPA affects the amount of studying?
The amount of studying affects your GPA.
Certainly. Of course, if your GPA is low, you might start studying more, right? So it's possible, or maybe you just say, I don't care anymore, I'm going to study less, right? Both of them are possible. So the point is that chances are that it's your studying habits that affect your GPA, not vice versa. Which means one of those is called the explanatory variable, and the other one is called the response variable. The explanatory variable is the one that explains the reason for the response. So in my example that I just gave you, it's the amount of studying which affects the GPA. So the amount of studying affects what your score is going to be, what your GPA is going to be. I would say that the amount of studying is going to be your explanatory variable, and the GPA is then the response, like cause and effect. But, here's a very important thing. Statistics cannot answer the question of cause and effect. I'll give you an example. It has been statistically shown that people who own more cars live longer than people who don't own a lot of cars. The more cars you own, statistically, the longer you're going to live. Does that mean that if I really wish to live longer, I should go out and buy a few extra cars? Does that seem reasonable?
No.
No.
But nevertheless, statistically, it's valid. People who own more cars tend to live longer. So why is it that people who own more cars tend to live longer, and you're telling me that I shouldn't go out and buy more cars if I want to live longer?
It's because people with more cars have more money, and it's like not related to their cars.
Well, if they have more money, therefore what? Why does that make them live longer?
Because they have more resources.
Say again?
Probably got better health insurance.
Okay, so there it is, right? So people with more cars tend to have more money. People with more money tend to have better access to doctors, hospitals, health insurance, and people with those who have access to those things are probably going to live longer. That seems reasonable, correct? Does that mean that having more cars causes you to live longer, or having more cars is just a reason why you would live longer? Which one is it?
Why?
It's a reason why. So statistics deals with correlation. Statistics asks whether or not one thing is connected to something else. Statistics does not say this thing causes this thing. That is not answered by statistics. You know what answers that? What answers the question of whether A causes B? It's called common sense, right? There's no mathematical way of showing that A causes B. It's just, think about it. Does it seem likely that A should cause B? Do I have a reason why A should cause B? If so, A causes B. But statistics answers the question of, are A and B connected? Does that make sense, everyone? So when you talk about the explanatory and response variable, one thing is occurring as a result of the other. It's true, but not necessarily because one causes the other, but rather because they're connected. Now, in the case of the GPA, it seems very likely that the more you study should have an immediate response on your GPA, and that A causes the other. But that's common sense. That's not math. That's not statistics. Does that make sense, everyone?
Yeah.
Okay, anyone not following that, or not agreeing with me, or not sure what I'm saying? Or I got a thumbs up, which is always nice, and then lots of just names. Okay, so the primary purpose of what we're going to be doing is to predict one variable from knowledge of another, or possibly more than one. For example, I can't predict exactly how tall a baby is based upon their age, but I can probably get a good ballpark based upon lots of babies and their ages and their heights, right? I can get a general ballpark feeling for how fast they grow and how tall they should be at any time. In fact, we do that. Who here has a kid? I don't, thank God for them, but who here has a kid? Anyone?
I do.
Okay, you do. So you ever take your kid to the, as they're growing up and they're babies, and that, I don't think a nephew would count because you wouldn't yourself take the kid to the doctor. But if you take the kid to the doctor, they probably measure their height and say they're in the 80th percentile or the 70th percentile, something like that, right? How tall are they compared to other kids their own age? Something of that sort, right? I assume. Yeah. Okay. How do they get that? Because they have lots and lots of information about babies at that age. So they have a general idea of how tall a kid should be at that age. Right? And as such, if they have a general idea of how tall a kid should be at that age, then they can say, based upon all of the data that we have, this is where we expect the kid to fall. Your kid falls here, yada, yada, yada. So we use a lot of information to come up with a ballpark figure, and then we want to predict, okay, how tall should an 11-month-old baby be? Okay, well, according to data, this is how tall it should be, right? We want to predict based upon our knowledge of the relationship between the explanatory variable and the response variable. So, as such, we classify variables based upon their role. The explanatory variable is we're using it to predict or explain another variable. It's the x variable, the independent variable, the predictor variable, the one that predicts the other. And then we have the response variable, the one that's going to be explained or predicted itself. That's the y variable, the dependent variable, and so on. Make sense? Yes, no, maybe so?
Yeah.
Yeah.
Okay, so let's look at some examples. For each response variable, name some variables which might serve well as predictor variables. So unfortunately, this PowerPoint kind of like has the answers already. I couldn't find one that didn't, but let's understand why the answers are there. So college GPA. What are some things that might predict college GPA? Well,
Time,
sorry, say again?
study time and hours.
Okay, study time and hours. It's not there, but this is good. Do something that's not on the list. If you look at the list, there's two things there. The high school GPA, your high school SAT scores, current grades should probably have a good prediction on your future grades, how much time you're spending. These are all things that should predict. And if I was a statistician and I was sufficiently interested, I might do a study and try to figure out how well one thing predicts something else. What about the price of your home? Don't look at the answers. Let's see if you can do it without looking at the answers. What are some things that might predict the price of a home? Your zip code.
Square feet.
Right, location, square footage, right? Beverly Hills, Bel Air.
Floors.
Say again?
Floors.
The number of floors. Someone said something, I just couldn't hear it. What did you say?
Number of rooms.
Number of rooms, number of bedrooms, number of bathrooms, school districts, but I guess that's location. Cost of surrounding houses, that's a good one as well.
Oh, could you also say when it was built?
How old the house is, a homeowners association, and Melrose. What's Melrose? HOA I know because I have one, but what's Melrose? Is that something that I should know? That's something, I'm not sure what that is. Melrose? I'm not sure. I just know we pay for it. Well, I don't know what it is, but I believe you. I'm not sure. Anyone know what Melrose is? MELLO space ROOS? Melrose? I don't know what that is. Okay. Anyway, so here's some examples. Number of cars, let's go, number of cars owned. What do you think is a good predictor for how many cars you have? What are some things that might allow
Garage
us?
size.
Sorry, say again? The garage, well, garage size.
Garage size.
So someone said garage size. A few people say garage size. I like that one. But I would think that you buy a house based upon how many cars you have, and you don't buy a certain number of cars based upon the garage. But maybe it's there. I don't know. It's just an option. Income, certainly. You know, rich people, richer people might have more than one car. Whether it's close to a freeway, that's a great one, right? Whether it's close to a train station, maybe. The people in your house that need a car, it's a great example, right? Maybe kids, how many kids do you have? Because you want to get a car for every kid, right? Or, you know, every kid over 16 at least. Anyways, so sometimes there's more than one predictor for a given response, but we're going to focus on a specific predictor and a specific response and try to figure out if there is a connection between them. So let's look now at the next one, which is on scatter plots. The scatter plot is your basic picture of the relationship between one quantitative variable and another. Okay, this is your basic picture of how one quantitative variable is associated with another one. Okay. If you look, for example, on the next slide, the beer sales. So this is an example of a scatter plot. Okay, you have temperature and beer sales at Yankee Stadium, and you took a sample of 10 games. So after 10 games, we calculated the beer sales and the temperature. Which one do you think should predict the other? Would temperature predict beer sales, or beer sales predict temperature?
Temperature predict beer sales?
I would imagine so, right? It's not like God is watching and saying, you know, if you believe in God or the great turtle in the sky, whatever. But it's not like he or she is watching and saying, oh, there's that many beer sales, let me fix the temperature, because it doesn't seem reasonable. But when it gets hotter, people want to drink more beer. That seems reasonable. In fact, if you looked at the scatter plot, would you say that that is represented by what we might think, that the higher the temperature, the more beer sales there are? Does that seem that the scatter plot represents that relationship? Look at the scatter plot, please, and tell me whether or not you think it represents that relationship.
Yeah, it does.
It seems to, right? Because it's going up. So as you go to the right, it goes up, right, up. That means that as one gets larger, the other one gets larger. Now, a big question that we're going to have is whether or not the data is linear. Linear means that the data falls on a line. Now, it's never, unless it's, you know, an amazing coincidence, it's never going to fall precisely on a line. It just, the world does not work that way with uncertainties, okay? Because not everyone drinks beer. So you can't just say, oh, the temperature went up a little, more beer is going to be sold. It doesn't work that way. It's just a general idea. Does this data come across as being linear?
Yes.
Would you say, as a general rule, it falls on a line?
Yes.
It certainly seems, if I share my screen here, right? If I share my screen and I annotate and I draw, right? I'm not sure how good this is going to be, but, you know, it certainly seems that the data approximately falls on a line, correct? Yes? No? Maybe so? Actually, you know what? I could probably draw a line here. Can I draw a line? I can draw a line. Hold on. Crazy talk. How's that? No, I don't like that one. No better. Okay, how's that? Does that seem relatively accurate?
Yeah.
Now, do the points actually fall in a line? No, they don't. Do they approximately fall in a line? Yes. We're going to come up with a mathematical way of how close the points are to actually falling on a line, so that we don't gotta eyeball it and say, yeah, I think so, or no, I don't think so. We're going to have a very mathematical way of doing it. In fact, we're even lucky because Crunch is going to do it for us, so we don't have to do it ourselves. But we're going to come up with that. So a scatter plot is and this is the previous slide, if you go back a slide, a scatter plot is a graph which displays the relationship between two quantitative variables, always quantitative, never categorical. The explanatory variables on the x-axis, the response variables on the y-axis, and each individual appears as a point on the scatter plot. So 10 individuals in the example that we did, 10 points on the scatter plot. Viewing a scatter plot is an important preliminary step that should be made before any statistical analysis of the relationship between two quantitative variables. This is very important. Before you start plugging things into formulas, make a scatter plot. Check to see whether or not you expect the data to be linear. Sometimes you might get the mathematical result that the data is linear when it's not even close to being linear. But if you just do the math, but you don't really see what you're doing, you're never going to notice that. So it's very important to always do the scatter plot first. Okay. Let's take a 5-minute break here, 5:07. We'll come back at 5:12 on my clock. And we will then finish today's lesson. Sound good?
Yeah.
I can't talk for too long. I need a drink. We can end the lesson now. No need to flex the bills on. Oh, you guys saw that? Sorry, there was a couple 20s. It wasn't a lot. Just I had a couple 20s just lying there. I just trying to clean up a little bit. I got stuff all over the place that I'm trying to organize. I'm never very good at the whole organizing thing. I got things all over the place. That's a lot of money to us college students. Yeah. Yeah, I remember the college days. I used to work in my in the science lab in my school, setting up labs for classes. Oh, it's like $8 an hour or something like that. That's crazy bad. What's minimum wage these days? What do you guys make? Anyone here work on college?
13.
Huh?
13.
13? Yeah, I would have killed for 13 back then.
15.
15 in LA. Good times, good times. Some places are still 10.25. It's crazy, right? 10.25.
Yeah.
So I mentioned that I'm not really into politics at all, but which parties want to increase minimum wage and which parties don't? Is there an answer to that question?
Typically, liberals want
Democrats.
higher.
They want
Go ahead.
Democrats want higher, you said?
Yeah.
And Republicans wanted to say the same?
Yeah.
Well, I can certainly understand why people would want it higher. So what is the reason? I'm not saying it's stupid. I'm just saying, what is the reason why Republicans want to keep it the same?
Because they think that a higher, I guess, minimum wage is going to inflate the economy, and then cost of living is going to readjust to the minimum wage, and then we're going to be back at square one and just cause.
So in other words, there's no point, except it's going to ruin everything for everyone.
Right, and then we'll be stuck in kind of a vicious cycle.
Interesting.
Yeah.
I wish I knew enough about economics to know whether that was correct or not. I just don't. I mean, it sounds very logical. So I guess then the question goes back to the Democrats. Why do you want to increase minimum wage in light of this theory? So do they have an answer? Anyone have an answer for why the Democrats do want to increase minimum wage, even though this seems to be very logical?
I think it's to like make sure everyone's at least making enough to live.
All right, but the logic behind this is that if they increased it and you make more, cost of living goes up, and it's essentially you're back to where you were before.
Yeah, I mean, honestly, I'm not really into like I'm not really in any party, but I've just heard a lot of things about them wanting to just make sure everyone has enough to like survive.
And I think that's wonderful. I just whoever, I don't know who said what he just said, but whoever said that about it increases the price of everything, so basically nothing changes. It seems very illogical, and so I just want to know how those who want it to go up respond to that. So I guess it's because in states like California, the minimum wage is not enough. But if the minimum wage goes up, will the cost of living then increase as well, so that really no change was made? I don't know. I'm not bashing one side or the other. I'm trying to understand, because I just don't. But anyways, it's a math class. We had a few minute break, so I asked, but it's beyond my understanding. So I just teach statistics, which is easy for me, and I let all the smart people worry about real world problems. I'm not smart enough for that. So let's go to the next slide. And by the way, I wasn't even being facetious. To me, math has always been really easy. It's just something I've always been good at: math, stats, physics, chemistry, stuff like that. Real world things, I don't have a head for. There's too many variables, no pun intended, going on, and I can't see the correct path. Whether it's one side or the other, it's just so hard for me. But math is just pure. There's no complications to me. So I really, when I say that, I really mean it. Math to me is easy. This stuff is really hard. So if you guys know this stuff, more power to you. All right. Anyways, evaluating scatter plots. So it says always draw a scatter plot so you can visually assess the following characteristics. Jealous? I'm jealous of you guys. You're jealous of me. For me, math is easy, but what can I do with it? I once took my car to a mechanic, and he's explaining to me, how to fix it, and I have no idea what he's talking about. He goes, I thought you teach physics. And I go, yeah, I teach physics. He goes, well, this is all physics. And I go, yeah, but it's applied physics. I know physics. I know pure physics. There's no debate in math, right? Just everything's one answer, and there's one way to get it, and it's straight, and the real world is, I can't do it. That's why I stay home all the time. All right, anyways, the important characteristics of a scatter plot. So there's 4 basic things when you're studying scatter plots that you want to look out for. 1 is the form. The form is basically one question. Does it look like a line or not? That's it. Okay, if it's not a line, we really don't even care what it is. Okay, is it a line or is it not a line? Now, in more advanced courses, if it's not a line, what can we do with it? Sure, in that case, we really do care what it looks like. But as far as we're concerned here, line or not, linear or not. Once you've established that it's linear, then is it positive linear so that it's heading upwards? Or is it negative linear so that it's heading downwards? Or maybe it's even flat, okay? We want to know the direction. Positive, linear, neither. So it's linear. Step 1, great. It's positive, it's going up. Step 2, great. Now the question is, how strongly is it going up? Is it really tight along a line? Or is it very loosely along a line? And we'll see some pictures coming up of the difference between a really strong linear versus a moderate linear versus a weak linear situation. Those are the 3 possibilities: strong, moderate, or weak. So strong positive linear, moderate positive linear, weak positive linear, same things for negative. And then there's the 4th one. Once you have the general form, direction, and strength, are there any outliers? Is there anything that doesn't seem to fit with the rest? Those are the 4 things that we're on the lookout for a scatter plot. So let's look at the next slide. Okay, and the next slide shows us 6 scatter plots. The first one, would you say that that's linear, the first one?
Yes.
I would hope so. Is it positive or is it negative?
Negative.
Negative. Strong, moderate, or weak?
Strong.
Strong. Any outliers?
No.
Not a single one. Second one, linear or nonlinear?
Linear.
Linear. Strong, moderate. First, positive or negative?
Positive.
Strong, moderate, or weak?
Strong.
It's still pretty strong. It might not be as strong as the last one. So somewhat moderate. And that's fine. Luckily, we're actually going to come up with a mathematical way of determining strength so that we don't have to eyeball them. Okay, but strong or moderate, I can see both answers. How about the third one, linear or nonlinear?
Linear.
Okay, it still seems like a line. You still get the general gist of it. How strong?
Moderate.
Moderate. Okay, I can see moderate being correct. Positive or negative?
Negative.
Negative. Are there any outliers?
Not really, no.
Not really. Everything seems to fall along the line. Next one, linear or nonlinear?
Non-linear.
So yeah, it kind of seems like it's just a blob of points, right? It's labeled as linear, but I don't really see it as being linear. But again, you have to be careful because how closely zoomed you are can make something that's linear appear nonlinear and vice versa. So we're going to get to the math, okay? But if it's nonlinear, it certainly does not look linear. Then we don't even talk about strength and direction. It just, don't go to question 2 if you can't pass question 1. And the last 2, are those linear?
No.
No, they certainly do not look linear. The first one looks very parabolic. Second one looks very exponential. So once they're nonlinear, again, we don't care about anything else. Okay. The next slide already answers the questions of positive, negative. Again, I don't fully agree with this slide. You really only care if it's linear. So we have negative for the first, positive, then negative. The other three are not really linear, so I really wouldn't describe them. But I can see how even in that situation you might say one. So the second one on the bottom goes down and then it goes up. The third one is always going down. The first one, I mean, if I had to take a guess, it certainly looks like it's going up, but really it's the linear ones that we care about. And then the next slide is the strength, right? So they actually call the first one perfect, but for me, it's just very strong. Perfect, very strong, strong, weak. And then you have very strong and strong, but again, if they're not linear, we really don't care. If they're not linear, nothing else matters, and we really don't even talk about it. So again, not really agreeing with the PowerPoint and not going to be asked questions on tests where you have to worry about that. So let's now look at the next slide, which is unusual observations. So on the x-axis, the explanatory axis, we have the percent taking the SAT. And on the vertical axis, we have the mean SAT math scores. Okay, and what you see here is a general trend. Well, what is the general trend in that example when you see the top left? For me, I don't want to say it out loud. You guys tell me. What is a general trend in that first graph? Would you say it's linear or nonlinear?
Non-linear.
Well, it's kind of hard to answer that, because if the very two on the top left are outliers, cover up the two on the very top left. Would you claim it's linear now if you covered up the 2 or 3 in the very top left?
Yeah.
So maybe they're outliers, in which case it certainly seems linear. But if they're not outliers, then it seems a little curved, right? So
Yeah.
this is where math doesn't always have the answer for you. You got to determine, are they outliers or are they not outliers? And that will help your analysis of the problem. Again, don't expect problems where you have to worry about questions like that. I'm just pointing them out to you as we come across them. Okay? But in that example, it says South Carolina, North Carolina, and Georgia have the lowest mean SAT math scores. You can see them in the bottom right. And these scores are over 100 points less than the states with the best mean scores, right? 580 on the very top, all the way down to 440 on the very bottom. So the question is, what accounts for this? Why are those three so low in comparison? And it's not because, the people in the South, they're dumb. It doesn't make any sense, right? There's smart people and dumb people everywhere. So what accounts for this? I don't know. I mean, I can certainly hypothesize a possibility. Maybe people in those states are much more like, I don't know, I can't even think of it.
Rural states.
Huh?
They're rural states.
And therefore what?
Therefore, the education and schooling is not as adequate as it is in urban and suburban states.
I think it's like the funding.
That could very well be. Again, I don't know enough to answer a question like that. I'm not arguing. I'm not saying you're wrong. It certainly seems reasonable. If I was someone in the government, I might take an analysis like that and then try to get them more funding, if that was the reason why, right? Or try to raise their educational levels. Here we see how statistics can affect government policy, right? You do a statistical analysis of something, you get a result, you come up with a reason for that result, you check whether your reason makes sense, and if it is, policy changes because of it. That probably happens on a daily basis at various levels, but again, I don't know anything about that. I focus on the math. But you can see how statistics can be very, very important in the grand scheme of things, correct? Does that make sense?
Yeah.
Okay. How about on the right? What do we see here? What we see here is that we have a graph of the percent voting in 1980 Democrat, I'm sorry, the percent voting Democrat in 1980 versus the percent voting Democrat in 1984. Does it seem likely that if you voted Democrat in 1980, you're going to vote Democrat in 1984? Does that seem like a reasonable, does it seem reasonable?
Yes.
Sure. But Georgia seems to be a little outlier there, does it not?
Correct.
Right, Georgia certainly seems as if it went from 60% Democrats in 1980 or 58, 56 Democrats, I can't even tell exactly, but about 55%, and then it dropped to under 40%. So that certainly seems like an anomalous result, correct? And
Yeah.
as a statistician or as someone in politics or sociology, I might say, okay, what caused this? Maybe Georgia, maybe the president in 1984, the Republican candidate was from Georgia. And because the Republican candidate was from Georgia, maybe people who would normally vote Democrat decided to go for their state guy. I don't know. Is it a possibility? Maybe. What do I know? I don't know politics. So let's look at the next slide now. Right? I mean, does that seem reasonable that people would vote for a person based upon whether he's just from their state or not? I don't know. I don't know what makes people vote for anything. What do I know? All right, let's move on to the next one. All right, I can teach the math, but I leave the analysis of the math up to people who are smarter than I am. Okay, so which is stronger? Look at these two scatter plots. Don't look at any of the wording on the left of the page. Try not to look at their explanations and have that affect how you answer. Just look at the two scatter plots and tell me which one do you think is a stronger correlation, the one on the top or the one on the bottom? So type in your answers. Let's see what people say. We haven't really had any good questions so far in this PowerPoint. So let's do that now. So which is stronger? I see a lot of people, in fact, everyone so far. Oh, so someone saw it. Someone saw it. Most people said the bottom. A few people said the top. And one person said, well, they look pretty much the same with one zoomed in. And if you look at the scale, right, if you look at the scale, the first one goes from 60 to 140, correct? Well, 60 to 140 is only a very small portion of the second one. In other words, these are really the same data. They're completely the same data. It's just when you zoom in, two things which look very different are really the same. And therefore, this should be a warning to you to always trust the math. We're going to learn the mathematical way of computing the answer for how strong it is. And when we have the answer, that's all we're going to need. Okay, does that make sense? So the point is that we need a mathematical connection, because without a mathematical connection, we can't do anything. You can't trust what your eyes see, because your eyes don't always see what's actually there. Okay, I remember once I was once attending a physics talk. This guy flew in from some other state, was giving a talk, and he puts on the board a picture of what he claimed was an electron photograph of a molecule. And he starts talking about all of the things that he sees in this photograph at the molecular level. And everyone's like, oh yeah, that's good. Well, I see that's true. And he says, okay, well, just so you should know, this was actually taken from the plane as I was flying here. And he zoomed out, and you see it was like just a landscape, just like forest and whatever. But because of the zoomed nature of the picture, he zoomed in so much that it looked like it was just a blob of, and who knows what it was. So he lied to us, but it was to make a point. Always check your sources. Make sure you know what you're looking at. In this case, they were looking at the same thing in the top and on the bottom because the scale is different. If you look on the bottom, it goes from 0 to 250. and the top goes from 60 to 140, right? Big, big difference there. But really it's the same data, which means if you look at the next slide, we need to have a numerical measure of association between two variables. And to that end, since we only have like 8 minutes to go, right? 5:40 class is over, is that correct?
Yeah.
Yeah, so since we only have 8 minutes, I don't want to start with the actual numerical measure because I couldn't get far before having to stop. So we are going to stop here just with the need for a mathematical measure, and we will pick this up on Thursday. Okay? Yes? Is there a question? No question. Okay, so we will end here, and I will stick around. I'm going to stop recording.